Hi all, welcome to another video of the subject Power System Analysis based on KTU syllabus, and we are on module 6, and today we are going to discuss the power angle equation and power angle curve of the synchronous machines. And as we know, we have already learned the sync equation and the equation relating the electrical power generated, that is PE, to the angular displacement of the rotor, that is delta, okay, is called power angle equation. Okay, so this is PE, electrical power generated, it is PE, and the relation between that PE and delta, okay, it is called power angle equation. So the power angle equation can be derived using the transient model of the generator. Okay, that is, we are mainly using the transient model of the generator because the stability studies, the transient model of the generator is mainly used. Okay, for stability studies we are using the transient models, and you can see the transient model here. This is the transient model of the generator, and in that it is represented using an EMF EG dash, and there is an reactance XD dash is here. Okay, so transient internal EMF EG dash is the, and transient reactance XD dash is the. Okay, and for the analysis purpose, just consider a single generator supplying power through a transmission system to a load or any large system. Okay, that is, this is, consider this as the one end and this is the another end. Okay, we are supplying the power from this end, and in this end we may be connecting a synchronous motor, or it may be an infinite bus. Okay, infinite bus. So, and this rectangular box, okay, this rectangular box representing the linear passive components in the transmission line, that is mainly the reactance of the system. Okay, so here it is denoted as E1 dash is equal to transient internal voltage of the generator bus at 1. Okay, and E2 dash is the voltage at the receiving end. Okay, and they are saying that it may be the voltage at the infinite bus or the transient internal voltage of synchronous motor. And we are having a matrix equation for a two-bus system. That is, you may be already learned that system, a two-bus system. I think you may know. Okay, we can represent the two-bus system using the equation. This I is equal to Y bus into V. That is, the Y bus is the corresponding admittance matrix, and the expanded form here you can see, that is I1 I2 is equal to matrix Y11 Y12 Y21 Y22 and into the matrix E1 dash into E2 dash. Okay, where the currents I1 and I2 are the currents injected by the sources E1 dash and E2 dash respectively, and from the row 1 of the matrix we can write the equation I1 is equal to Y11 into E1 dash plus Y12 into E2 dash. Okay, that is the equation from the row 1. And also we know the complex power. Okay, the complex power S1 can be written as S1 is equal to P1 plus JQ1. Okay, that is, we know that the complex power can be written as P plus JQ. Okay, we are using the same equation here, so P1 plus JQ1, and that complex power, okay, it will be equal to E1 dash into I1 conjugate. Okay, E1 dash is the corresponding transient internal voltage of the generator to bus 1. Okay, but bus 1, and I1 is the corresponding current injected by that source. Okay, so E1 dash into I1 conjugate is the complex power. Okay, so for representing the complex power we are using that conjugate term here. Okay, and by substituting for current I1, okay, that is, in the previous equation we know the equation of current I1 is equal to I1 into Y11 into E1 dash plus Y12 into E2 dash. That equation is going to substitute in the equation 5.33. Okay, so we will get P1 plus JQ1 is equal to e1 dash into, instead of this y1 dash, sorry, i1 dash, we are substituting this y11 e1 dash plus y12 e2 dash. Okay, and by rearranging that terms, it becomes e1 dash into y11 conjugate into e1 dash conjugate plus y12 conjugate into e2 dash conjugate. Okay, because this conjugate is for all this time. Okay, this is i1 conjugate. We are substituting the value of i1 here, so the conjugate will be distributed for all the times. Okay, and we will get by simply rearranging the terms, e1 dash and e2 dash are here. Okay, e1 dash and e1 dash conjugate is written nearby, and e1 dash into e1 dash conjugate into y11 conjugate plus y12 conjugate into e1 dash into e2 dash conjugate, and this equation, and from that we can simply write the magnitude. Okay, we are only considering the magnitude terms here, okay, for e1 dash, so we can simply write this p1 plus jq1 is equal to e1 dash square. Okay, this e1 dash square into y11 conjugate plus y12 conjugate into e1 dash into e2 dash conjugate. Okay, nothing more, that is we have just rearranged the above equation here. Okay, and the corresponding quantities e1 dash, e2 dash, y11 and y12 in the equation are complex. We know that it is they are the complex quantities. Okay, so that can be represented using the polar coordinates or rectangular coordinates. Okay, so here the e1 dash and the e2 dash are representing in terms of the polar coordinates, that is e1 dash angle delta 1 and e2 dash angle delta 2. Okay, and the same likewise y11 and y12 can be represented in the rectangular coordinates as g11 plus jb1, and y12 can be represented as g12 plus jb12, and in the polar coordinates they are representing using modulus of y1 angle theta 11, and y12 can be represented as modulus of y12 angle theta 12. Okay, and actually we are going to substitute these values. Okay, these values, okay, in the above equation p1 plus jq1 equation. Okay, that is actually we are going to do, and in the next slide you can see that. Okay, so the p1 plus jq1 can be written as in the previous equation. We know that e1 dash square into y11 conjugate. Okay, this is the equation, e1 dash square into y11 conjugate. So instead of this y11, okay, we are substituting this equation, and also for e1 dash and e2 dash we can substitute the equations. Okay, so here p1 plus jq1 is equal to modulus of e1 dash square. Okay, modulus of e1 dash square, that is the magnitude only we are considering, into g11 plus jb1 conjugate plus instead of this y12 conjugate we are substituting y12 angle theta 12. Okay, it's polar, we are substituting in terms of polar coordinates. Okay, y12 angle theta 12 conjugate into e1 dash, okay, modulus of e1 dash angle delta 1 into mod e2 dash angle delta 2 conjugate. Okay, so that is all the terms. Okay, all the terms in the previous equation, that is e1 dash square into y11 conjugate plus y12 conjugate into e1 dash into e2 dash conjugate. Okay, so all these terms are written in terms of polar and rectangular coordinates. Okay, here this e1 dash square is already in the magnitude value. Okay, so we are not changing that value, and for all other quantities we are substituting this polar or rectangular coordinates here. Okay, and thereby we are getting that equation here. Okay, and we know that in the next step this modulus of e1 dash square into g11 minus jb1, because this g11 plus jb1 all conjugate, we know that it is equal to g11 minus jb11 plus y12 angle minus theta 12, because y12 angle theta 12 all conjugate. Okay, conjugate will give us the modulus of the value and then negative angle. So modulus y12 angle minus theta 12 into mod e1 dash angle delta 1 into mod e2 dash angle minus delta 2. So here also the same thing, that is the conjugate. So the conjugate is converted into the negative sign for the angle. Okay, and we are just rearranging that terms in the next step. Okay, that is thereby we are consolidating the angle here. Okay, we are having the angle minus theta 1 to delta 1 and delta 2. Okay, so they are written together here. So angle delta 1 minus delta 2 minus theta 1 2. Okay, and in the next step we are converting that angle. Okay, this term, this actually we can say that this polar coordinates into the corresponding rectangular coordinate in terms of that's cos and sine. Okay, cos and sine, that is cos theta plus j sine theta form. Okay, so so here the angle theta delta 1 minus delta 2 minus theta 1 2 can be written as, okay, that the this entire term can be written as, that is mod e1 dash into e2 dash into mod y12 cos delta 1 minus delta 2 minus theta 1 2 plus j, the same term, that is mod e1 dash e2 dash into mod y12 into sin delta 1 minus delta 2 minus theta 1 2. Okay, that is we are just writing that terms, that is this and their polar coordinates in terms of the corresponding rectangular coordinates. Okay, that is we can simply write an example for p angle theta. Okay, if we are having a rectangular coordinate, sorry, polar coordinate as p angle theta, we can simply write p cos theta, okay, plus j p sin theta. Okay, so likewise here we are writing that equations here. Okay, and next, in the next step we are simply comparing the real and imaginary part of the equation 5.35. okay, so by comparing the real terms, so in the left hand side we are having p1 plus jq1, on the right hand side we are having this equation. Okay, this entire equation. So if we are comparing the real term, we know that the real term here, okay, real term here in the right hand side we are having the real term as mod e1 dash square into g11. Okay, and here in the second terms we are having the real term as this term. Okay, and we are writing p1 is equal to mod e1 dash square into g11 plus mod e1 dash into mod e2 dash into y12 into cos delta 1 minus delta 2 minus theta 12. Okay, and if we are equating the imaginary terms, okay, that q1 will be equal to, okay, in the left hand side we are having the q1. So if we are equating the imaginary terms, we will get the q1 will be equal to, in the first, okay, in the first time we are having the imaginary term as this minus j is here, so that b11 into mod e1 dash square. Okay, that is minus e1 dash square into b11, and the next imaginary term is this term. Okay, plus e1 dash into e2 dash into y1 into sin delta 1 minus delta 2 into theta 12. Okay, and that equations, okay, the previous two equations, that is real and imaginary time equations, are equations of real and reactive power injected by the generator at bus 1. Okay, and we are just substituting some values here. Instead of this delta 1 and delta 2, we are going to substitute the term delta, and instead of this theta 12 minus pi by 2, we are substituting the term that gamma here, and mod e1 dash square into g11 pc, and instead of that mod e1 dash into mod e2 dash into y12, we are having p max, and for instead of that pe, okay, instead of that p1, we are going to substitute the term pe. Okay, so if you are substituting that terms in the previous equation, okay, that is equation, if you are considering that equation 5.36, okay, if you are having the equation 5. Instead of this p1, okay, instead of this p1 we are having pe. Okay, pe, so here we are having pe, and also instead of that mod e1 dash square into g11, we are having pc. Okay, this term we are having that pc. Okay, and for that mod e1 dash into e2 dash into y12, we are having P max. Okay, P max, and cos delta 1 minus delta 2 minus theta 1 2. So delta 1 minus delta 2 can be written as delta. Okay, and that theta 1 2 can be written as gamma plus pi by 2. Okay, so we are having the equation as Pe plus Pc plus P max cos delta minus gamma minus pi by 2. Okay, and that P is equal to Pc plus P max into sin delta minus gamma. Okay, that is this pi by 2 cos pi by 2 that time can be converted into the sign change. Okay, sign. So we will get the equation as that is a power angle. It is the actual power angle equation. Okay, so the power angle equation P is equal to Pc plus P max into sin delta minus gamma. Okay, so in this equation the term Pc represent the power loss, okay, in the system, and the P max represent the maximum real power that can be delivered by the generator to an infinite bus. Okay, and actually in this case the bus 2 is considered as an infinite bus. Okay, infinite bus, and we can simply substitute. Okay, simply take the value of delta 2 as 0 because it is considered as an infinite bus. So the delta 2 value can be taken as that 0 here. So in that cases, okay, in that conditions, that this delta is equal to delta 1 minus delta 2 becomes delta is equal to delta 1 only. Okay, that is actually saying in this slide. And the power angle equation can be further simplified by considering the network as a purely reactive network, actually by neglecting the resistances. Okay, so when the resistances are neglected, that we know that G11 becomes 0. Okay, that G11 becomes 0, and that theta 1 2 become pi by 2. Okay, if you are considering that, if you are neglecting that resistances, okay, G11 becomes 0 and the theta 1 2 will become pi by 2, and so that equation, okay, that is our equation gamma. Okay, that is this gamma is equal to theta 1 2 minus pi by 2. So if theta 1 2 is equal to pi by 2, then the value of gamma becomes 0. Okay, becomes 0 here. So if you are substituting that values, okay, if you are substituting that values in the power angle equation, that is in the previous equation, P is equal to Pc plus P max into sin delta minus gamma. So we will get the equation. We can simplify the equation as P is equal to P max sin delta. Okay, because the Pc, the term Pc will become 0. Okay, because that Pc is mod E1 dash square into G11. Okay, if G11 is 0, Pc becomes 0. Okay, and also we know that that term, okay, that term gamma becomes 0. Okay, so the equation becomes that power angle equation becomes P is equal to P max sin delta, where P max is equal to we know that the equation mod E1 dash into mod E2 dash into Y12. Okay, the equation is Y12, P max equal to mod E1 dash into mod E2 dash into Y12, but that Y12, it is admittance matrix, so it can be written as the X12. Okay, that is the reactance. Okay, transfer reactance matrix as X12. Okay, that is 1 by, that is that Y12. Okay, mod Y12 is equal to 1 by that X12. Okay, so we are substituting that values here. So the P max is equal to mod E1 dash into mod E2 dash into X12, where X12 is the transfer reactance between bus 1 and 2. Okay, and the power angle equation, okay, that the previous equation is the simplified equation, that is P is equal to P max sin delta is the simplified power angle equation. Okay, and we are having the power angle curve. Based on that equation, we can draw a graph between the power developed PE, okay, power developed PE versus this delta. Okay, and delta. So we are getting that curve as like this. Okay, this is the power angle curve. So based on the different values of delta, we are having that developed power PE. Okay, so the maximum power P max, okay, is located at the angle pi by 2 here, and here this is the typical power angle curve. Okay, and thus on substituting the expression for P, okay, from equation 5.39 in the Singh equation. Okay, actually we know that the Singh equation is Okay, we have already learned that equation, that is h by pi f. Okay, h by pi f into d square delta by dt square. Okay, it is equal to Pm minus Pe. So if you are substituting that Pe as P max into sine delta, okay, so we can represent that Singh equation, okay, expressed as a function of delta. Okay, so the Singh equation is changed as h by pi f into d square delta by dt square equal to Pm minus P max into sine delta. So here instead of Pe, okay, we are substituting that P max minus P max into sine delta here in the Singh equation. Okay, so this is the power angle curve, and this is the Singh equation expressed as a function of the angle delta. Okay, okay, I hope all of you understand the portion well. Okay, so here we have derived the power angle equation. Okay, power angle equation as P is equal to Pc plus Pmax into sine delta minus gamma, and it can be further simplified as P is equal to Pmax into sine delta. Okay, and if you are substituting that equation in the Singh equation, the Singh equation becomes h by pi f into d square delta by dt square is equal to Pm minus Pmax into sine delta. Okay, so that is the derivation. I hope all of you understand well. So thank you.